Okay, does everybody have their notes pulled up? Now, I know this says Chapter 2, Section 5, Transformation of Functions, and 2.4 obviously comes before 2.5, but the way that the notes are put together, it was parent functions of 2.4, and then piecewise, and then transformations the next day. I want to do all the functions together, and then we'll do piecewise tomorrow. So you guys have 2 PDFs for homework, day 1 and day 2. They are both due on Friday. Tonight's homework is a little longer, so that's why I'm giving you guys a little extra time. Tomorrow's is shorter, the lesson is shorter, so you guys should have extra time. But there's 2 assignments that are due Friday morning. Make sure you guys are aware of that. Everybody see that? Okay, do we have our notes? Okay. This is the beginning of talking about different kind of functions. You guys are familiar with 2 different functions already. You're familiar with linear. What kind of a shape does the graph of a linear function make? X to the first power makes a line. Good. Does anybody know what the shape of x squared makes? It's a parabola, a quadratic. Then we have something called cubic functions. That's x to the third. We have the cube root function. That's the cube root of x. We have a square root function, and we have the absolute value. You guys need to memorize the characteristics of these parent functions, what the graph looks like, what their domain and range and all that stuff is. You guys are going to need to know that. When I say a cubic function, you need to, in your mind, go, oh, okay, I know what the shape looks like. So let's look up here at absolute value. All right, my absolute value function makes a V. Anytime you have absolute value, your function will make a V shape. This is the parent function. We're going to do transformations to it. We're going to flip it over the x-axis and the y-axis. We're going to stretch it and shrink it and move it up and down and left and right. But just the parent function is what your picture here looks like. It's at the origin, and it's a positive V going upward. So let's talk about our domain. What is the domain for this function? What can I use for x values? Everything. Negative infinity, positive infinity. My domain is negative infinity to positive infinity. I can use anything I want. There's no restrictions. Looking at your graph, guys, and what do we know about absolute value? What are the y values that you could get out? If I plug in, think about this. If I plug in, let's plug in -1, 0, and 1. Let's plug it right in here. What's the absolute value of -1? 1. What's the absolute value of 0? 0. What's the absolute value of positive 1? 1. What's the absolute value of -12? 12. What's the absolute value of -14,000? 14,000. So what is my range going to be? Greater than or equal to 0. It's going to be starting at 0. It will include it and go all the way up to infinity. Say it again. Just plugging in numbers. So let's talk about increasing and decreasing. Increasing means the graph is going what direction? Up. Decreasing means it's going down. Okay. So what is this graph doing? As we read left to right, my absolute value. From left to right, what is your absolute value graph doing? It's decreasing from where? Negative infinity to 0. Then it's increasing from 0 to infinity. Perfect. And what is the interval of constant? None. You could say none or NA. Absolute value graph is going to make a V. Now again, we're going to talk in a minute about how it can be shifted up, down, left, right, flipped over the X, flipped over the Y, that sort of a thing. But your parent function for absolute value is just a V. All right, sound good? All right, I'm going to move down here to quadratic. Quadratic is x squared. You guys are familiar with this. This is called a parabola. It's not parabola, it's parabola. Now, your absolute value graph and your quadratic graph are very similar. Do you guys see the similarities in their parent functions? The shape is almost the same, correct? That means all of this stuff, all of our characteristics, is basically the same. What's my domain for x squared? What can I put in for x squared to evaluate it? Do I have any restrictions? No, I can put anything I want, right? I can put any negative number. I can put in any positive number. I can put in 0, and I'll get an answer out for y. So what's my domain here? Negative infinity to positive infinity. Now let's think about our range. Let's throw in some values here.
I'm sorry, this relates
Because 0 is included. What's the absolute value of 0? If I plug in 0 for x, what do I get out for y? Because when you plug in x if you plug in 0 for x, you get out the value 0 for y. It's a solution. So let's talk about x squared. What happens when I plug in -1 to x squared? What do I get? +1. What happens when I plug in 0? 0. What happens when I plug in +1? 1. What happens when I plug in -5? 25. What happens when I plug in -10? 100. What happens when you plug in any negative number and you square it? It becomes positive. So what is my range in this case? Bracket 0 to infinity. I'm not going to get anything below 0. In my parent function, if you square a negative number, you'll never get anything below 0. So again, when I look at increasing, decreasing, constant, we read left to right on the x-axis. What is my parabola doing? The exact same thing my absolute value graph was doing. It's decreasing from where? -infinity to 0. Perfect. And then what? Increasing from 0 to infinity. And then is there an interval of constant? No. Very good, guys. Very good. So now we're going to scoot on over here. I'm going to scoot over to the cubic function. Why do you think this one is called a cubic function? Because it's being cubed. Perfect. It's x cubed. The shape of your cubic function, Miss Corey calls it a wiggle. I call it a vertical snaky thing. Right? That's very technical, right? It sounds real mathy. It makes a vertical snaky thing. But let's think about this. Do I have any domain restrictions? Are there any numbers I cannot use for x? No, I can use anything I want. So what would my domain be? -infinity, good, to +infinity. What's my range here? Look at the graph. What's my range from low to high? -infinity to what? +infinity, good. Let's talk about increasing, decreasing, constant. Let's talk about increase, decreasing, constant. Let's plug some numbers in here. What happens when I plug in -1, 0, and 1? When I plug in -1 cubed, what does that give me? -1, okay? When I plug in 0, what does that give me? 0. When I plug in 1, what does that give me? 1. So what this graph looks like, it's kind of hard to see here. Hold on. So at -1, we're at -1, so -1, 0, and then 1, 1, something like that. I know on the graph it looks a little different, but is there an area of decrease in this graph at all? No. What's it doing the whole time? It's going to be increasing from -infinity to +infinity. Your decrease and constant are none. How could that be different? Well, what if the negative was out in front? It would be -x cubed, and it's exactly the same characteristics of a linear function. It just has a little wiggle in the middle. Now, when you do shifts and stuff to it, I know. All right, now we're going to get to where we have a little bit of a different look here. Why do you think this one's called the square root graph? Because the x is where? Underneath the square root. So that's what the picture of, we sometimes call this a little wave. It's like a wave. The parent function starts at the origin. So let's think about what my domain is and what my range is. This is a square root function, correct? So I'm going to plug in -4, 0, 1, and 4. What's the square root of -4? 2i, okay. What do we know about that? It's imaginary, right? What's the square root of 0? 0. What's the square root of 1? What's the square root of 4? 2. So what do you think my domain is for my square root function? Can I use any number in the whole world? No. Where do I have to start my values at?
0.
Why? Because if it's less than 0, what do you get? An imaginary. Very good, guys. So your domain, and it includes 0. You can use 0. Totally fine. Square root of 0, 0. That's fine. So think about that. If the smallest number I can use is 0 for my x value, then what's the smallest number I can get for my range? 0. Very good. From left to right, what is this graph doing the whole time? It's increasing. Good. Is there any area of interval of decrease or constant? No. It may look like it gets a little flat as the numbers get closer and closer together, but it'll never be just flat. I'm sorry. You're right. Right here. From 0 to, yeah. My bad. Thank you. 0 to infinity. All right, now let's look at the cube root function. Why do you think this one's called the cube root function? Because it's underneath the cube root. Now, how does this cube root, how does green compare to red? It's like sideways, right? One's vertical, one's horizontal. What is x cubed and the cube root of x? What are those two of each other? They're inverses, right? All of these things, guys, all of them have some sort of relationship. If you look at your parabola, think about it. Vertical parabola up and down. Look at the square root. That's the inverse, right? Doesn't it look like just half of a parabola, but it's turned on its side? All right, so let's talk about, just look at this graph. You guys should be able to tell me some stuff. What's the domain? What can I use for my cube root? All real numbers. I can use anything. I can use anything negative, because you could have the negative. You could take the cube root of a negative number. So what happens for my range? If I can use any number in the world, I can take cube root of negative, I can take cube root of positive. Can I get answers that are negative and positive? Yes, so what would that be? Negative infinity to what? Positive infinity. Now, it may not look like it does it a lot, but what is this graph doing the entire time? It's increasing from negative infinity to positive infinity. There is no area of constant. All right, now I understand this is very abstract. What I need you guys to take away from this is to be able to look at the shapes of the graph and say, oh, that makes a V, it's absolute value. Oh, this is x squared, it's going to make a parabola. Oh, it's x cubed, it's going to make the vertical snaky looking thing. Right? I need you guys to be able to visualize those things. We're now going to talk about how we can use them. How we can shift graphs, all right? We're going to use shifts, it's called shifts, to move graphs around. There's vertical and horizontal stretching and shrinking. There's reflections. And there's going to be shifts moving it up and down and left and right. Now, you can identify these shifts from looking at the equation itself. Why is this important? Because if you are given a question on the SAT, the PSAT, a test in here, and it's a multiple choice. You have to pick the graph. On your website, you should pick the graph. You don't have to plug in points. You can use this knowledge and say, okay, because it says +1 here, I know the graph is moving up. Because it says -1 inside here, I know it's moving to the right. Something like that. So let's look. And I know I said minus moving right. You'll see when I get. Here are our shifts. All right, vertical shifts. What I want you to notice. Here is my function. What function is this? Absolute value. What's this one? X squared parabola. What's this one? Square root. Good. What is this one? Cube. What is this one? Then what? Then what? Then what? Okay. What I want you to notice, to move a graph up and down, where does your shift occur in regards to the function itself? Outside of it. And you're doing what? Are you adding and subtracting? Are you multiplying? Are you dividing? What are you doing? If you add or subtract, now it could be out in front, it could be 3 plus, whatever, but if you add or subtract a number to the function, that is your vertical shift. Plus and minus the function, it moves the graph up or down. Now think about this. If it's plus, which way does the graph move? Up. If it's down a number, which way does it move? I mean, if it's minus, which way does it move? Down, okay? So if you had like x squared plus 3, think about what that looks like. What does x squared make? What shape of a graph is x squared? It's a parabola, and where does it move? Up 3, right? You should be able to visualize that. Oh, it's a parabola, it moves up 3. It's a positive parabola. It's a happy one, so it's up. We'll talk about negatives in a second here. The more we do this, you guys will be fine, I promise. So think about this, all right? Our original parent function for a parabola is something like this. I'll do it in blue. Now again, yes, you guys could plot points and plug in and say, okay, if I plug in -2, -1, -0, you know, whatever. But what does this shift do? What does this +2 at the end do to our blue parabola? It moves it up 2. Good, so it would look like this. This is what I want you guys to do. I want you to visualize what's going to happen, and I want you to sketch it. I do not want you plotting points. All right, again, I have a parabola. It's x squared. I'm going to go right here to my parent function. And in this case, where are we moving? Down 2. 1, 2, so it's going to go this way. That's a vertical shift. Vertical shifts move your function where? Up and down. Okay, good. Very good, ladies and gents. Okay, so now we have horizontal shifts. Well, when I think horizontal shifts, where are we moving? To the left and to the right. Look where horizontal shifts occur. This is inside the absolute value. This is inside the parentheses with x squared, correct? This is underneath the radical. Where do horizontal shifts occur? Outside of the function or inside? Inside, okay? It moves the graph left, the number of spaces, it moves the graph right, the number of spaces. Look at that for a second. Is there a typo in this? All of these are what sign in the middle? Positive, but it moves the graph which way? Left. Doesn't it make sense that if it was positive, it would move to the right? And if it was negative, it would move to the left? Okay, it's just the opposite. Whenever you have something inside of a function, I'll show you at the end, I'll show you why. But you need to remember horizontal shifts occur. Is occur 2 C's, 1 R? Okay, inside. Say inside, and it's opposite of what you think. And I'll show you why in a second. Opposite of what you think. So here, look, all this is minus, 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 minus. So you think it would go left, but it's really going to go which way? Right. Vertical shifts are exactly what you think. If it's positive, it goes up. If it's negative, it goes down. Horizontals are left and right, and it's the opposite of what you think. So when we look at a question, all right, just look at this for a second. Before you start anything, guys, tell me what number 3 looks like. What shape is that? It's a parabola, and it's moving which way? 2 to the left. Good.
Wait, I have a question.
Yep. Squared. So here my original would look something like this. And I know it's 2 to the left. So I'm going to say left 2. You guys are going to say, how would I show my work? Exactly what I just did there shows your work. I circled the 2 to say, oh, it's a parabola. I put a little arrow that says, oh, it's inside, so it's the opposite of what I think. So this actually moves this way. It doesn't move up or down, just moves left and right. Does that make sense? Every time you have one of these, and the more you do it, the easier it gets. After a couple days, you're going to, we talk about this in pre-cal, we talk about this, and so this isn't going to go away. But again, look at the shape of your graph. What is this? It's a parabola. Okay, so here's your parent functions, what the normal one looks like, the mom and dad. And then this bad boy is going where? To the right too. Good. And I'll show you why again at the end. I want to make sure I get through everything. All right, let's look at this next one. What is this shape? It's a shape, a worm, a wiggly looking vertical thing, right? So your parent function is something like this. So what does this -1 on the outside of my function do? It moves it down 1. If it's inside parentheses, if it's underneath the radical, if it's inside the absolute value, That's when we go left and right. If it's outside, not affecting the function other than a plus or minus, that's when it moves up and down. So this one just goes down one. Well, I hope I don't lose my voice. I know you guys are hoping I lose my voice. But all right, what do you notice about 6? First of all, what's the shape? The snaky, wormy thing. Good. The vertical one. How many transformations do we have in this one? 2. What is this graph going to do? It's going to go up 1 and to the left 2. Very good. You could do this in 2 steps if you wanted to. You could go left 2 and draw it and then go up. But if you want to, you can just go ahead and say, okay, from the origin, I'm going to go left 2 and up 1. So my graph looks something like this. How do we feel?
Are we going to have to draw both on the test, or are we just going to fit
I have absolutely no idea. I will find that information out and let you know. Let's look. Let's keep going. Graph each function. Before I even start, I like to do this. I like to say, okay, what am I dealing with? This is a cubic, right? So I know in my mind it's that shape, that wiggly looking thing. What does this minus 3 do? It goes right 3. Anything inside parentheses with the x is the opposite. And then what does this do? It goes up 2. Perfect. So if you guys want to, here's my parent. Just a little sketch. Now again, this is not as obviously as accurate as if you plugged in all of your table of values, but at least you can get an idea of what the graph looks like. This moved right 3, so 1, 2, 3, and up 2. So something like this. What's the shape of number 8? It's the square root. That one looks kind of like a wave, kind of. So think about where this graph moved. My original was at the origin, and it just goes like that. Something like that. What does this one do? What's the plus 2 mean? Up 2. Good. And then what is this negative 3 on the inside? Right 3. Good. Very good. So it goes up 2, 1, 2, and right 3. 1, 2, 3. So something like that. But you see why this is beneficial if you have a test and you're saying, oh, I have to pick the graph. Instead of going through and plugging in all these values, all you have to do is identify the transformations and then check. All right? What shape is this graph? Parabola. What's this one? The V. What's this one? Snaky thing. Vertical one. What's this one? The wave. Okay? Now, where do you notice, guys, the negative is? It's on the outside, okay? It's on the outside. If your negative is out in front, on the outside, you're going to flip across the x-axis. So think about where the x-axis is. The x-axis. Oh, that's cute. The x-axis is here, correct? So if your graph exists in the top, if it's reflected, where is it going to exist? Down. So think about it. If you have a negative parabola, your positive parabola, it's happy. It's going in what direction? Up. So a negative 1 is going to be flipped which way? Down. I want you guys to think about this in terms of linear. What kind of a line do I have here? Is that positive or negative? It's positive because it's sloping which way? Up. So if I have a negative line, which way is that line going? Down. The exact same thing occurs for your transformations here. If you have a negative out in front, it flips over the x-axis. So where, guys, do you have a negative that flips it from left to right? Instead of top to bottom, left to right. Where does the negative need to be? Inside. That will move it from the left side to the right side, or vice versa. Okay, so let's practice a little bit. Before you start, think about all this stuff, okay? What is the shape of this graph? It's a parabola, okay? So it's like a U shape. Now there's 2 transformations going on here. I have a negative out in front, and I have a plus 2 at the back. What is the negative out in front going to do? It's going to go over what? Over x. So because, think about that. A negative parabola is going downwards. And then what does that plus 2 mean? It's going to shift up 2. So your parabola, your new one, after your transformations, your vertex goes up 2 and it's flipped over. It's downwards. It's sad. Yep.
Why is this one over the oh, because there's a negative.
The negative out in front flips over the x.
Wait, but it's the blue.
That's the x-axis.
Oh.
The blue went up and then flipped down.
But don't you go down 2 and then up 2? Wouldn't that go back to 0?
No, you go up 2. There's no down 2. All right, look at the shape of number 10. My original is that wave looking thing, right? Where does this flip my wave? Across the y, from left to right instead of up to down. So this is over y since it's inside. So your reflection would be like this. Now, how can you check to make sure, guys? You can plug in points. But what we're trying to do now is to be able to identify all of these transformations just by looking without having to make a table of values. First, negative 1 squared is 1 and then times it by 2. Sure. All right, one more thing I'm going to talk about. One more thing, and then we're done. What's going on here? There's a constant in the front. Are you adding or subtracting that number?
No.
We're multiplying, right? Anything on the outside, right? That's not on the inside, underneath the radical in a parenthesis. Anything on the outside has to do with your vertical. If you are multiplying by a number greater than 1, it's a vertical stretch. What that's going to do is it's going to make your, think about like a rubber band, right? Like I have a parabola like this, and I'm multiplying it by a positive whole number. It's going to stretch, it's going to make it skinnier. If you want to say that, you can call it skinny. It's going to make it skinnier. So what do you think multiplying by a number between 0 and 1?
It's gonna make it wider.
It is going to make it wider. It's called a vertical compression or shrink. It's going to make it fatter, going to make it wider. It's like you're taking your hand from the top and smushing it down. So if my normal parabola looks like this, and we'll plug in values here so you can see it. If you have a vertical shrink, it's going to be skinnier. It's going to be more like this. All right, let's think about our table of values just to compare so you guys can see. For blue, if I plug in negative 1, 0, and 1, what's negative 1 squared? 1 times 2 is 2. Well, I should have done that in yellow, right? That's what I was trying to do. Plug in 0. 0, 0, okay. And then I plug in 1. What's 1 squared? 1 times 2. So think about that. Instead of your blue, when you plug in negative 1 into x squared, it's 1. Instead of you going out and up 1, here you go out 1 and up 2. It's going to make it skinnier. So the other thing that's going to happen here, if you have your normal parabola here, if you multiply by a half, you're going to smush it down, so it's going to become wider. It's going to shrink it. A vertical stretch is like you're taking whatever function it is from the top, from the y-axis, and pulling it. You're stretching it, making it skinnier. A compression is going to smush it down. Yes, ma'am?
How come 2 times negative 1 got 2?
Because you have to square the number. All right, what's going on here? What's the shape of this graph, first of all? It's the square root. It's just a square root graph. Where is the negative sign? It's out in front. If it's out in front, what do we flip over? Over the x. So your reflection would look something like that. You just take it and flip it down. What did I create? A sideways what? Sideways parabola, okay? Now, The reason why the stuff inside the parentheses is negative. I mean opposite. So we have this. You guys do not need to write this down. Okay, we're going to get to something later on. This is called vertex form. We have standard form and we have vertex form, all right? Vertex form is for, this is in a parabola. How do I know this is a parabola? Because it's squared, okay? This is where your shrinks, your vertical shrink and stretch occurs. If I could spell. This is where you're up and down, right? Your vertical shifts up and down. And this on the inside here is where our horizontals occur, correct? Left and right. Agreed? Inside the parenthesis. What sign is inside here? Negative. So if I were to plug a positive number, right? If I wanted to say 3, if I plug it in here, what does it look like in the formula? It would say x what? Minus 3. If I were to say, I want to move this thing right 3 units, I would plug a 3 in right here. Well, what does it look like in the formula? It looks like a minus. If I wanted to move it left 3, I'd say, okay, well, I'm going to plug in a negative 3. Well, what happens when you have minus and negative? It becomes positive. So once we get to vertex form, this will make a little more sense. But it's because in the original equation, there's a minus inside, so it changes the sign of the inside. Does that make a little bit of sense? Okay, so your homework tonight, you guys can start on it. It's just a bunch of these. It's identifying the parent function, and then it's shifting stuff. It's moving it around. My suggestion to you is to identify in words first. Draw arrows. Okay, this is going to shift this way. This is going to move this way. And then draw the picture. Try to draw it without using a table of values. If you want to use a table of values to check, that's fine, but you don't have to. Tomorrow, we're going to do piecewise functions. Anybody seen piecewise before? It's really simple. It's just graphing, like graphing lines and stuff like that, but you don't want the whole graph. You just want a piece of it. So it'll be easy peasy, promise.